Off the coast of Northern California, there's a spot where 3 tectonic plates were supposed to meet. Scientists just found out there are actually 5, not 3 plates. 5 moving pieces, and 2 of them were completely hidden until this year. That changes how experts think earthquakes could strike this entire region. Stay with me, because what these hidden pieces are doing right now is the real story. Hit subscribe right now, because this channel breaks down real science, not fear. Let's start with where we are talking about, because this location matters more than almost anywhere else on the west coast of the United States. Off the coast of Humboldt County, California, near the small city of Eureka, there is a point on the map called the Mendocino Triple Junction. For decades, geology textbooks have described it the same simple way. 3 massive tectonic plates meet at this one spot. The Pacific Plate, sliding northwest against the North American Plate to form the famous San Andreas Fault to the south. The Gorda Plate, which is really just the southern piece of the same Juan de Fusa Plate that drives the Cascadia subduction zone, diving underneath the North American Plate to the north. And the North American Plate itself, sitting in the middle, absorbing pressure from both directions at once. Before going further, it helps to understand the basic difference between the 2 types of faults meeting at this junction, because they do not behave the same way. And that difference is a big part of why this spot is so complicated. The San Andreas Fault is what geologists call a strike-slip fault, meaning the 2 sides of the fault are sliding horizontally past each other, like 2 hands sliding past one another on a table. The Cascadia subduction zone, on the other hand, is a thrust fault, or where one plate is being forced underneath the other at an angle, building up vertical pressure that releases upward and outward when it finally breaks. Strike-slip earthquakes and subduction thrust. Earthquakes tend to produce different patterns of shaking, different types of aftershock sequences, and in the case of subduction events, they are what typically generates large tsunamis because the seafloor itself gets pushed upward. Right at the Mendocino Triple Junction, you have both of these very different kinds of tectonic motion happening within just a few miles of each other, which is a major part of why modeling this region has always been so much harder than modeling a simpler single fault system further south along the San Andreas. This is not just some random intersection. It is one of the most seismically complicated and most dangerous points anywhere in North America, because it is the exact spot where 2 of the continent's most famous and most feared fault systems physically connect. To the south, you have the San Andreas Fault, responsible for some of California's most destructive earthquakes in history. To the north, you have the Cascadia subduction zone, capable of producing a magnitude 9 megathrust earthquake, and they both meet and interact right at this one junction off the coast of Humboldt County. For a long time, scientists studied this area using the simple 3-plate model because that is what the surface data seemed to show. But in January 2026, a team of researchers from the United States Geological Survey, the University of California, Davis, and the University of Colorado Boulder published a study in the journal Science that completely rewrote that picture. Here is how they did it, and it is a genuinely clever piece of detective work. Instead of relying only on the big earthquakes that people actually feel, the research team focused on something almost nobody pays attention to: tiny, low-frequency earthquakes. Tremors so small and so deep that they never reach the surface in any noticeable way. These tiny quakes tend to arrive in clusters, called swarms, and they carry information about what is happening far below the surface, in places regular earthquake monitoring struggles to see clearly. By carefully tracking thousands of these small, unfelt tremors using seismometers spread across the Pacific Northwest, the research team started to notice a pattern that did not fit the old 3-plate model. There appeared to be additional pieces of crust moving independently underneath the junction, pieces that had never been mapped or accounted for before. To make sure they were not imagining a pattern that was not really there, the scientists used a fascinating verification method. They checked their model against ocean tides. Every single day, the gravitational pull of the sun and the moon puts a small amount of stress on the Earth's tectonic plates, the exact same forces that pull ocean water back and forth to create tides. When that pull lines up with the natural direction a plate is already moving, it tends to produce a few more of these tiny tremors than usual. So the team compared the timing of thousands of small earthquakes against the timing of these tidal forces and checked whether the pattern matched what their new 5-piece model would predict. It did. The tremors lined up almost exactly the way the model said they should, giving the researchers strong confidence that what they were seeing deep underground was real, not just noise in the data. So what did they actually find hiding down there? The team discovered that south of the Triple Junction, the Pacific Plate is not simply sliding past the North American Plate the way older models assumed. It appears to be dragging an older piece of rock underneath the North American Plate as it moves north. Researchers named this newly identified piece the Pioneer Fragment. At the same time, north of the junction, something else unusual is happening. A separate piece of the North American Plate itself appears to have broken off. and it is being pulled down and subducted along with the Gorda plate rather than staying put the way the simple three-plate model assumed it would. Add those two newly discovered fragments to the three plates everyone already knew about, the Pacific, the North American, and the Gorda, and you get 5 separate independently moving pieces of crust, all interacting in an area barely larger than a mid-sized American county. One of the lead scientists on the study compared the discovery to studying an iceberg. Everyone had only ever been looking at the small visible part sitting above the surface. This new research was the first real look at the much larger, much more complicated structure hiding underneath. There was another detail buried in this research that deserves attention. The team also found that the subducting surface of the Gorda plate sits shallower than existing models had predicted. If that sounds familiar, it is because a very similar discovery was made further north along the Cascadia subduction zone in Oregon earlier this same year, where researchers found the Juan de Fuca plate interface sitting about 5 kilometers shallower than expected, directly increasing predicted shaking intensity along that stretch of coast. Now, a comparable pattern is showing up at the southern end of the same fault system, right at the Mendocino Triple Junction. A shallower fault interface generally means the source of a future earthquake sits closer to the surface, which tends to translate into stronger shaking for the communities sitting directly above it. Why does any of this actually matter for people living in this region? Because earthquake hazard models, the ones used to design buildings, retrofit bridges, and plan emergency response, are only as good as the underlying map of what the crust actually looks like beneath the surface. If the real structure underneath the Mendocino Triple Junction includes 2 additional moving fragments that were never part of the original models, then the stress calculations built on top of that old 3-plate picture may be missing something important. One of the study's co-authors, a professor at UC Davis, put it plainly, saying that without properly understanding the underlying tectonic processes in a region like this, it becomes much harder to accurately predict the seismic hazard people there actually face. To understand why this region deserves this level of attention, it helps to look at what has already happened here, because the Mendocino Triple Junction is not some quiet, theoretical risk. It has a violent track record. On April 25th, 1992, at just after 11 in the morning, a magnitude 7.2 earthquake struck near the small town of Petrolia, right in the same Triple Junction region. The shaking lasted only about 9 seconds, but in those 9 seconds, it produced some of the strongest ground acceleration ever recorded in California history, over 2 times the force of gravity at one measuring station, strong enough to throw a heavy piece of parked machinery into the air. The main shock alone caused tens of millions of dollars in damage, badly damaging over 1,000 structures across communities like Ferndale, Petrolia, Rio Dell, and Scotia, injuring several hundred people and triggering a small tsunami recorded as far away as Crescent City and Humboldt Bay. And the shaking did not stop there. Less than a day later, 2 more powerful aftershocks, magnitude 6.5 and 6.6, struck the same region within hours of each other on faults running through the Gorda Plate itself. That 1992 sequence became a landmark moment in West Coast earthquake science because it proved in real time that the plate boundary near this triple junction was capable of producing damaging earthquakes on its own, separate from a full Cascadia megathrust rupture. It also happened just 5 years after a geologist named Brian Atwater had first published evidence that the Cascadia subduction zone to the north was capable of producing giant earthquakes at all, a discovery that had been controversial at the time. The 1992 earthquake reinforced that warning and helped push forward the creation of California's own tsunami preparedness programs. And this is not just ancient history from the 90s. This junction has kept producing significant earthquakes right up to the present day. In December 2021, 2 magnitude 6 earthquakes struck near the Mendocino Fault. A year later, in December 2022, a magnitude 6.4 earthquake hit near Ferndale, close enough that researchers found evidence of small but real aftershock deformation reaching down into the subduction interface itself, suggesting the shallow strike-slip faults and the deep megathrust below them are not as separate as scientists once assumed. Then, on December 5, 2024, the region produced its largest earthquake in over 2 decades, a magnitude 7.0 rupture along the Mendocino Fracture Zone, about 35 miles offshore of Cape Mendocino, at a depth of roughly 10 kilometers. The shaking from that 2024 earthquake was some of the strongest ever recorded in a California earthquake, with the most intense shaking measured in the town of Rio Dell. It set off an aftershock sequence with well over 300 recorded events in the following weeks, and remarkably, a magnitude 4.3 earthquake struck on the Mayakama Fault, a branch of the San Andreas system, nearly 180 miles away, just 3 minutes after the main shock. Researchers who studied this event noted that a rupture of this size was large enough to redistribute stress across the junction, adding pressure onto both the northern San Andreas Fault and the southern end of the Cascadia megathrust at the same time, exactly the kind of stress transfer scenario that makes this location so difficult to model with a simple three-plate picture. This research examined a magnitude 7 earthquake on that fault and found something that should concern anyone thinking about earthquake early warning systems. Even with dense modern seismic monitoring networks watching the area closely, the earthquake produced almost no detectable foreshocks or slow slip warning signs beforehand. It essentially went from silent to rupturing with very little advance signal at all. That matters, because a lot of hope around future earthquake early warning technology rests on the idea that faults usually give some kind of subtle signal before a big rupture. This particular fault, sitting right at the edge of the most complex tectonic junction in the region, appears capable of skipping that warning phase almost entirely. Put these pieces together and you start to see the full picture of why this specific patch of the California coastline gets so much scientific attention. You have a newly discovered 5-plate structure instead of the simple 3-plate model everyone learned for decades. You have a shallower than expected fault interface, similar to the pattern just found further north in Oregon, which tends to mean stronger shaking. You have a documented history of damaging earthquakes striking with almost no warning, as recently as 1992, and again highlighted in the newest 2026 fault behavior research. And you have this entire junction sitting at the exact meeting point between two of the most significant fault systems in North America, the San Andreas to the south and the Cascadia subduction zone to the north. This last point deserves its own explanation because it connects directly back to research we covered in earlier videos about Cascadia. Scientists studying earthquake behavior at this junction have started asking a bigger question. Could stress transferred through this newly mapped, more complicated 5-piece structure actually help trigger earthquakes on one of these two major fault systems after a rupture begins on the other? Researchers describe stress transfer in this region as exceptionally complicated, precisely because of how many separate moving pieces are packed into such a small area. If a large earthquake on the Mendocino Oceanic Transform Fault or elsewhere in this junction were able to transfer meaningful stress onto the southern end of the Cascadia megathrust or onto the northern end of the San Andreas Fault, that raises the uncomfortable possibility of one earthquake increasing the likelihood of another following close behind it, rather than these systems behaving as completely separate, unrelated hazards. A separate, long-term statistical study of the region, published in early 2026 and covering more than 4 decades of earthquake data from 1984 through early 2025, broke the junction down into 3 distinct zones: the deep subducting Gorda slab, the shallower Mendocino Transform Fault zone sitting above it, and the northern San Andreas Fault system to the south. Each of these 3 zones, the researchers found, behaves differently in terms of how often earthquakes cluster together, and how often a smaller quake acts as a foreshock warning of a larger one to come, versus simply being an isolated event or an aftershock, trailing a bigger quake that already happened. This kind of detailed statistical mapping is exactly what feeds into the newer 5-plate model, because it shows that treating this junction as one single uniform hazard zone was always going to miss important differences in how each piece of the underlying structure actually behaves. None of this new research is telling us that an earthquake is coming next week, next year, or even within a specific predictable window. That is worth repeating clearly, the same way it needs repeating for every story like this. What the 2026 studies are actually doing is replacing an oversimplified textbook picture with a far more detailed and far more accurate one, revealing additional moving pieces, a shallower fault interface, and a documented tendency for this junction to produce earthquakes with little to no advance warning. That is not a prediction of doom. It is scientists finally getting the tools, in the form of ultra-sensitive seismometers and 13-plus years of accumulated tremor data, to see structures that were always there, but were simply invisible to older technology. So what does this actually mean for the people living along this stretch of the California and southern Oregon coast, in towns like Eureka, Ferndale, Fortuna, and Crescent City? To put the scale of this region in perspective, it helps to step back and look at the northern San Andreas fault system as a whole, because the Mendocino Triple Junction is not an isolated curiosity. It is the northern anchor point of the same fault system that runs all the way down through the San Francisco Bay Area and beyond. The San Andreas Fault is famous for producing the 1906 San Francisco earthquake, a rupture that started near this same general stretch of coastline and tore southward for hundreds of miles, destroying much of the city and killing thousands of people. Scientists have long understood that stress along the San Andreas system does not stay neatly contained in one place. It can transfer along the fault over time, and the northern end of that system, right where it meets the Triple Junction, is one of the least understood segments of it, precisely because the tectonics there are so much more complicated than the more thoroughly studied sections further south near Los Angeles and the Bay Area. That is part of why researchers specifically flagged stress transfer as a serious open question in this newest round of research, because a fault system this significant, anchored to a junction this structurally complex, is not something regional planners can afford to model with outdated assumptions. It means the updated science coming out of this research directly feeds into how emergency planners in Humboldt County and across Northern California think about earthquake and tsunami risk. Just like the updated Cascadia hazard models we covered previously, a more accurate underground map leads to more accurate shaking predictions, which leads to better informed building codes, more targeted bridge retrofits, and clearer tsunami evacuation planning for the communities sitting directly above this junction. The 1992 Cape Mendocino earthquake already proved that this region does not need a full Cascadia megathrust event to produce serious, costly damage. A rupture confined to this triple junction area alone is capable of shaking Humboldt County hard enough to knock homes off their foundations and start fires, and it can do that in under 10 seconds, with next to no warning beforehand. There's also a broader economic angle worth understanding, because Humboldt County and the surrounding North Coast region depend heavily on infrastructure that runs directly through or near this junction. Highway 101, the main coastal highway connecting Northern California to Oregon, crosses this seismically active zone, along with regional ports, timber industry infrastructure, and the electrical grid, serving tens of thousands of residents spread across small coastal towns that often have limited alternate routes in or out during a disaster. The 1992 earthquake alone caused tens of millions of dollars in damage and left entire communities without basic services for days. A future rupture involving a more complex, better understood fault structure does not necessarily mean a bigger earthquake than what has already happened here. But it does mean planners now have a clearer basis for deciding where retrofit funding, evacuation infrastructure, and emergency communication investment should be prioritized first, rather than spreading resources evenly across a model that we now know was oversimplified. It is also worth understanding what scientists are doing right now to keep refining this picture further. The Northern California Seismic Network, along with expanding offshore monitoring efforts similar to the ones used along the Cascadia Fault further north, continues to record data every single day from this junction, feeding directly into the kind of long-term statistical and structural studies covered here. Researchers have specifically called for denser instrumentation directly above the newly identified Pioneer fragment and the subducted North American plate piece, since both were only detected indirectly through tiny tremor patterns, and direct measurement would sharpen the model even further. This is slow, unglamorous work, drilling cores, placing sensors, running years of statistical analysis on earthquakes too small to ever make the news. But it is exactly this kind of research that turned a decades-old, oversimplified three-plate textbook diagram into the far more accurate five-piece structure we understand today. If you live anywhere along the Northern California or Southern Oregon coast, the practical takeaways here are the same ones that apply to any earthquake-prone region. And they are worth repeating because they are simple and they work. Know whether your home or workplace sits inside a mapped tsunami evacuation zone, information that Humboldt County and the state of California make publicly available. Know your nearest route to higher ground, and remember that strong, prolonged shaking near the coast is itself the tsunami warning, since a wave generated by a nearby rupture could arrive in minutes, well before any official alert reaches your phone. Keep basic emergency supplies on hand, the same water, food, flashlight, and communication plan that applies to any major natural disaster anywhere. None of this is new advice invented for dramatic effect. It is the same guidance emergency planners in this region have given for years, and the 2026 research simply reinforces exactly why that guidance still matters, and maybe matters even more than the old three-plate model suggested. Here is the honest, balanced way to think about everything you just heard. The Mendocino Triple Junction has always been one of the most seismically active and complicated regions in North America, and the 1992 Cape Mendocino earthquake already proved it is capable of striking hard and fast with very little warning. What changed in 2026 is not the underlying danger of this region, it is our understanding of it. Scientists discovered that the simple three-plate model taught for decades was missing two entire pieces of moving crust. Found evidence the fault interface here sits shallower than assumed, similar to a pattern found further north along Cascadia, and confirmed through a separate study that quakes on the connected transform fault nearby can strike with almost no detectable warning signs at all. None of this tells us when the next earthquake will happen here. What it tells us is that scientists now have a far more accurate picture of what this junction actually looks like beneath the surface, and that accuracy is exactly what allows engineers, emergency planners, and coastal communities to prepare for what this ground is actually capable of doing, rather than the simplified version we used to believe. That is the real story here. Not fear, not a doomsday countdown, just careful, patient science, slowly revealing the true complexity hiding beneath one of the most important and most misunderstood earthquake zones on the entire West Coast. If you want more videos like this, breaking down real published research on West Coast earthquake hazards in plain, simple language, subscribe to this channel because there is more coming out of USGS, UC Davis, and CU Boulder on this exact region in the months ahead, and I will keep covering it as it happens. Drop a comment and tell me which part surprised you the most, the hidden pioneer fragment, the shallower fault, or the fact that the 1992 earthquake gave almost no warning at all. And if you know someone living along the Humboldt County coast or anywhere near this junction, share this video with them, because understanding what is actually happening under your feet is exactly the kind of thing worth knowing before you ever need it. Thanks for watching, and I will see you in the next one.